Okay, in the previous video we talked about how to encode numbers, natural numbers in lambda calculus, the church encoding of church numerals. And also we talk about how we can do the addition of two numbers and also how we can do the successor function. And today let's talk about how can we do the multiplication of church numerals. How this works? So you can see here this implementation of the multiplication function in the lambda calculus. What we do? We can see here that we need to provide some function which takes two numbers and output to us the multiplication of these numbers. And here in this type signature actually they represent the arguments for these two numbers, m and n. So we add m number and then n number and multiply them. What we need to return? They need to return the sum number which encoded in the church numerals, and they know that every church numeral has this started this type signature, so they provide it here. And after that, they know that the multiplication can be expressed via addition, and this means that they can use this m number to actually provide m times of addition of n. And before this, they need to apply to n the function f to somehow remove, to strip one level of the lambda signature. And this will have this, this will transform this into n times f, which represented as a lambda function which takes just x, and apply this x to this f. But after that you as a function put this into the m, and this m actually do somehow cloning of the n groups m times. I think to understand this we need to go to our lambda calculator. So what I need to provide multiplication function, and as I say, it takes some m, it takes some n, it takes some f. No, it actually not takes. This will be partial application here, and actually this what they will have on the output. This is the signature of our church numerals actually, but here. And we need to provide body. How we provide body? Actually, I say that they take m groups of n, for which we need to apply f, and after this apply x. And let's define it. Okay, let's check that I do all correct. Interesting why it's add this x not in the parentheses. Let's redefine. So I think I need no, I think that's okay. Yes. And now try to multiply. Okay. I will multiply 2 by, for example, 3. Let's see what we have. So we have this reduction process and it leads us to 6. Okay, it works. And what actually has happened? So at first we can see that our 3 encoded as expected this as this church numeral, our 2 encoded as this church numeral, and they have this body of our lambda function here, of our multiplication function. Actually, this is this body. After this, they do the first beta reduction. And we need, of course, to understand the evaluation strategy which implemented here. And here is implemented the normal reduction. Normal order reduction. This means that they chose at first the leftmost outmost term, and here this is actually this term, and to this term they do the application of this term. Actually they replace this x, not x, m. We replace this m with this term, and they do the substitution. Here we go to this thing. Of course, after that they do the next application. They choose this form and apply, replace the n with nf everywhere. Not sorry, not. This is they chose this form term and applied to this term. So this n is replaced here. Here it's stripped, we know n, but here they replace it with this thing. So this thing goes here. Of course, I understand that it is hard to read this thing, but at some point you will receive these 2 groups by 3. And you merge them. So actually, this order of evaluation hard to read, but I think main idea is to somehow squeeze with groups. Each group has the n church numerals, and it's just repeated m times, and after that squeeze into one church numeral.